Greetings, my young math Padawans. This is lesson 1.2, part 2. In this lesson, we're going to start talking about other transformations. So last time we focused on horizontal and vertical shifting. In this lesson, we're going to talk about reflecting over a line and stretching and shrinking, the reflection and the dilation piece. Let's get into it. First, reflections. So we're going to strictly focus on the reflection over the x-axis. Okay, and the form of that is going to be y equals negative f of x. For us, as I've told you, ours is going to look like negative the absolute value of x. When you see that, it simply means we're going to take our graph and we're going to reflect it over the x-axis, meaning instead of my v opening up, it's going to open down. That's the only thing that negative does. It just reflects it over top of the x-axis. It is worth mentioning that we could reflect over the y-axis, but that transformation is just not one we're going to talk about right now. So we can put that to our mind, know that it exists, but that's not going to be important for us right now. We can also do what we call a vertical stretch or a shrink. And the word stretch or shrink is simply going to be referred to based upon the value that our A value, which I'll get to here in a minute. So the general form for this vertical stretch or shrink is going to be in the form of y equals a times f of x. And for us, that means y equals some number times the absolute value of x. So you're going to see a number in front of the absolute value of x. When you see this, it basically means that our slope is going to change. And I'll show you that here in the next problem. But before we do that, it's worth noting that when the value for a is greater than 1, so think about like a slope of 2 or 3. Think about what that does to a linear equation. For us, what that's going to do is it's going to make this v look narrower. It's going to kind of make it kind of look a steeper line. We call that a stretch because it's almost like I took the two ends of a rubber band and pulled it up. It's almost like I took my graph, took the two ends and pulled it up. So a value for a greater than 1 makes my graph look much steeper, a closer V like this, as opposed to a value of a between 0 and 1. Notice nothing less than 0 because those would be negative numbers and then we'd get into the whole thing with the reflection. But if I did in fact have a value that was say like 1/2, like a value of 1/2 or 1/3, think about how gradual that makes a slope of a regular line. For my absolute value graph, that kind of makes it look like it's been flattened down. And it actually is a shrink. We call it a shrink because it is pushing down on my graph and kind of pushing it out. Let's see what these actually look like with transformation of an actual example problem here. So here in example 1, we're looking at g of x equals negative the absolute value of x plus 2 minus 3. Folks, what we learned last class is not going to be any different. This plus 2, remember what that means. That means that we move to the left 2 units. This minus 3, remember what that does. That means we move down 3 units. And now we have this negative sign that's right here. And that negative means that it's going to be reflected. Okay, for us, essentially what that means is my v is going to open downward. That's all it means. That's the only difference that we're going to have. So when we graph this equation, if we think about that parent function that we've been starting with, in order to graph our new function, we're going to take this parent function, we're going to move it to the left 2 units, we're going to move it down 3 units, and we're going to make that v open down instead of up. Now, I'm hoping at this point that we really don't even have to plot many more points. But this is what the graph would look like. And I'll label it g of x so that we don't forget that that's exactly what it is. A graph that has been moved to the left is down 3 and has been reflected, and now that v opens down. But what about a vertical stretch or shrink? Like what if there's a number in front of it instead of a negative sign? So we have 1/2 the absolute value of x minus 1 plus 3. Again, nothing's going to be different in regard to the minus 1. That's going to mean that we're going to move to the right 1 unit. The plus 3 means we're going to be up 3. But again, here we have this new part, this 1/2. So what does that mean? Well, I think the easiest way to think about that 1/2 is giving a slope to a line. It's a slope, and I'm going to put that in quotation marks. I'll explain why here in a minute. I'm going to say that it has a slope of 1/2. So again, I'll start with that parent function graph, and I'll think about that. And I'll think about that graph being moved, again, to the right 1 unit, okay, right 1, up 3, and that's going to give me my new vertex. Let me get rid of those lines. I don't want them to confuse us. So we moved to the right 1, we went up 3. Now let's talk about this slope in quotation marks of 1/2. Okay, what that means is if I had the normal parent function, without that 1/2, my graph would look like this. Right? But that's not what I have. In this problem, I have a kind of this slope, this idea of a slope to a problem. And if you think about counting it, the rise over the run, I would go up 1 and over 2. And I would go up 1 and over 2. If I only did this with half of the line, man, I'd be all the way over here. And that's not correct. That's not what I want to see. Instead, what I want to make sure I do is I want to make sure I have this V, the idea of a V. So I'm going to also go in the other direction. Now, I want you to understand this is different than having the slope of a linear equation, okay? This is an absolute value function. An absolute value must have a V. So we're going to kind of create this kind of V shape that has this, in quotation marks, slope of 1/2 in both directions. Hopefully that makes sense to you. Let's have you try a couple problems. So take an opportunity right now, and I'd like you to try these 2 example problems. See if you can come up with the graphs and what they look like. So pause the video right now, take a minute, sketch these 2 graphs on your own paper, and then when I come back, we'll go over the answers. So go ahead, pause the video right now and try these problems out. All right, for the first one, for letter C, that I've labeled letter C, you should be thinking right 4, up 2, and again, this slope of 3. And again, I put that in quotation marks. So we'll go to the right 4. We'll go up 2. That gives us our vertex. And now we'll plot our slope of 3. So we'll go up 3 over 1. Up 3 over 1, that's going to be off the grid. So I'll go in the other direction as well. And we'll create this V. What about for letter D? You should think in this problem that we're going to the left 3 units, up 4 units. Ooh, and look here, negative 1/2. So we got 2 things going on. We have a reflection, and we have a slope of 1/2. So let's get there. So we left 3, up 4, puts my vertex right here. And now I think it's really easy from here if we think of us going down 1 into the right 2, right? That's a negative slope. That's what a negative line looks like. And then I can just grab the 2 points on the other side of the V. And we can draw our line in. Folks, when I'm graphing absolute value functions, I see that kind of like that mirrored point on the other side. And that's because my absolute value graphs have something called symmetry. It's very important we don't ignore the idea of symmetry with these graphs. That's going to come back in a later lesson. I'm going to use that word an awful lot. So we've talked about transformations of functions and the 3 big things that we've talked about: horizontal and vertical shifting, reflecting over a line, specifically the x-axis, and stretching and shrinking. We can also perform transformations to functions that have already been transformed. And that's what the remainder of this video is going to be about. Let's take a look. So, for example, we have f of x equals the absolute value of x plus 3 minus 4. Let's take a look at what that graph actually looks like. You'll see that this graph has been moved to the left 3 units and down 4 units. Okay, so now we're going to perform a transformation to this function, not the parent function, but to the one we're actually looking at. And for this problem, we're going to take this and we're going to move it down 3 units. Okay, so what's that mean? Well, nothing different than what we've been doing before. We still take each individual point and move it down 3 units. Any point, take a point, pick a point, move it down 3 units. And once we get that, and again, as I did last class, add a couple extra points to this graph, we can use our ruler and we can draw our line to get what our new function looks like. We've moved it down 3 units. But mathematically, what is my new equation? Well, I didn't move anything to the left or to the right. Hold on, g of x. So that means it's still going to be the absolute value of x plus 3 because I didn't move it left or right. But my graph is down 3 units more. So what's that mean? That means I moved it down 3 units more. And if you think about it mathematically, that now gives me a new equation of x plus 3 minus 7. And that's the equation of my green line. Let's try another one. What if I take that same function, let me put it here on the graph, and what if now I move it to the left 2 units? Oops, let me get my highlighter there, my left 2 units. Okay, what's that mean? Nothing different. We're still going to take each one of these points and we're going to move them to the left 2 units. So left 2 units, left 2 units. Everything's moving to the left 2 units. So let's plot some points and see what my graph actually looks like. It becomes this nice orange line. But mathematically, what did we do? Okay, well, I have my equation that I started with, x plus 3 minus 4. I didn't move it up or down, but what I did do is I didn't move it to the left. And according to the transformations that I've done, when I add a number on the inside, that means I'm moving it further to the left. So that plus 3 is actually going to have incremented, or it's going to increase by 2 numbers. And my new equation is going to be the absolute value of x plus 5 minus 4. And if you look at it, if you look at your equation, you'll see that, yes, this orange line has, in fact, from the parent function, regular old absolute value of x, moved to the left 5 units and down 4. And my resulting equation is this new guy right here. Let's try another one. What if I take a function and I reflect it over the x-axis? Okay, we'll start with that f of x function. And now we're going to take this function and we're going to reflect it over the x-axis. Reflect it over the x-axis. What's that mean? That means every single one of these points that is below the x-axis now becomes above the x-axis. So for example, my vertex, which is right here, that is currently 4 units below the x-axis. When I reflect it over the x-axis, it becomes 4 units above the x-axis. So my vertex now moves to right here. The same thing with any point. So how about this guy that's right over here? He's 1 unit below the x-axis. He will now move 1 unit above the x-axis, and that's my new point. What about this point over here? It is 3 units below the x-axis. So he will now move 3 units above the x-axis. One more. Let's just do one more. Over here on this side, look at this point. This point is 3 units above the x-axis. When I reflect it over that line, he moves all the way down here, 3 units below the x-axis. And now if I get my ruler, I can add a couple more points because it's always a good idea. And now when I get my ruler and draw it, this is what my new function looks like. It is worth noting, look here, check out that guy that's on the x-axis. It stayed exactly in the same spot. 0 units above the axis turns into 0 units below the axis. What about my equation? What does my equation look like? Ooh, this one's a little tricky, okay? So let's look at it. F of x, let me do it in red. F of x equals the absolute value of x plus 3 minus 4. What we actually did was we took this entire equation and we reflected it. We made it negative. And if you think about what that does, with my new equation, that negative sign made it open down. We didn't move anything different to the left or to the right, so it stays the absolute value of x plus 3. But look at what happened. I'm no longer below. I no longer shifted down 4 units. It actually looks like I went up 4 units. And that's what happens when you reflect. The up and down piece changes. The left and right piece will not. Let's take a look at another one. One more. Write a function w whose graph is a transformation of all 3 of the above transformations. So we're going to do them all. Woo! We're going to do all of these transformations. Let's start with that parent or the original function f of x. Let's start with that one again. Okay, we're going to move it down 3 we're going to move it, let's see here, left 2. We're going to reflect it over the x-axis. Okay. Okay, let's try this here. Okay, so we're going to try to do it all at one time. So I'm going to take this vertex point right here. I'm going to take that vertex point. I'm going to move it down 3 units, okay? Down 3 units, 1, 2, 3, so that puts it right there. And I'm thinking about it, right? I'm thinking about it. Okay, now what? Now I'm going to move it to the left 2 units, okay? Left 2 units. That vertex is now here. And a little bit, again, I'm thinking about what my absolute value graph looks like, okay? And that's 6 units or 7 units below the x-axis. And that's important because now when I reflect it over the x-axis, that's 7 units below is going to become 7 units above. And I'm going to open downward instead of upward, which is going to give me a graph that looks a little something like this when it's all said and done. I ran out of grid, and that's why my graph is maybe not as neat as what yours will be when you use graph paper. But this is going to be the ending result of my function. I'll label it. It looks, I'm calling it w of x. That's what my equation is. But what does this actual equation look like? What is it going to look like? You know, I got to be, like, if I went through and did the math, I think you would see it, right? Because what am I going to do? I'm going to start with, let's start with it, f of x equals, I'm going to start with the absolute value of x plus 3 minus 4. And what's going to happen? Well, the first thing I'm going to do is I'm going to make sure that it went down 3 units. So that's going to be minus 3 units. And then I'm going to make sure I moved it to the left 2 units. Remember what that did? That added 2 inside those absolute value bars. And then what did I do? Then I reflected it. So what does that do? That makes the whole darn thing negative. The ending result will look like this. We'll call it w of x equals, we know we have that negative because we reflected. If you look at it, it looks like this is moved to the left 5 units, so that's the x plus 5. And it also went up 7. So 2 things, right? Here, the negative 4 minus 3, that turns into negative 7, but then we're going to multiply it by this negative 1. So actually is plus 7. Whew. That's going to be the equation. Now again, folks, if you don't need to think about the math, that's fine. We can actually look at the graphed function and create the equation. You practiced that on the lesson check from the last class. All right, time for you to try one. Let's see if you can try this one. We got multiple transformations that are going to be here. So f of x is equal to the absolute value of x minus 2. Okay, I would like you to write a function g who has a translation that was up 2 units to the right 4 units and reflect it about the x-axis. Give it a try. See if you can figure out what the graph looks like and what the new equation is going to be. So pause the video right now, give this one a try. Okay, I started here with my parent graph, and I'm going to take that, I'm going to move it up 2 units. Oh, I'm already off the graph, but I'm going to move it up 2 units. And then I'm going to move it to the right 4 units. Okay, let me think about where that is. I'm up here at 7. Moving it up, we'll put it here at 9. Moving it to the right 4 units. Let's see, I was already at 2. So moving it to the right 4 more units, we'll put it over here at 6. I got to go a little further, over here at 6. And now I'm going to take that point right there, right? So this is where my V is at right now. It looks a little something like that in my head. I'm going to reflect it over the x-axis. Man, this is the worst grid in the world to use, isn't it? But we're going to make it through. So this reflection over the x-axis, if I'm thinking about where this coordinate pair is, I'm thinking about where that coordinate pair is, I know that right now I am 6 units to the right, so at positive 6, and I'm 9 units up. So I know I'm at point 6, 9. So I'm going to reflect that over the x-axis. That's going to put me down here at negative 6, negative 9. I'm sorry, positive 6, negative 9. And when I do that, I know my graph is going to open downward. Boy, that's a horrible coordinate plane to try to show you this on, isn't it? But that's okay. We may do. You can see it. I'm sure it's going to be there. You're going to number yours better. I just know it. Okay, but let's go ahead and start with this. Let's see what the equation looks like, right? So we got f of x. We have the absolute value of x minus 2. We got the plus 7. And we're going to look at the transformations we did. right? So the first thing we're going to look at is we know that we went up 2 units. What's that do? The up 2 units adds 2 to my equation. Then what? Then we went to the right 4 units. What does that do? That moves it further to the right 4 units, right? That makes that subtracting a 4 there. And then finally, the last thing, what do? We reflected it over the x-axis. Remember what that does? That makes the whole thing the opposite of what it was. So when I write out my equation, g of x equals, I got the negative. I got the absolute value of x minus 6, and then I'm going to be minus 9. Whew. All right, folks. I thank you for watching. Thank you for paying attention. It's time to do some practice. Good luck.